Hey, and welcome back to Math 7195. We're still in Unit 7. Today we're going to continue on with confidence intervals. The confidence intervals we'll be discussing are for the population proportion, which we'll denote with the symbol pi. So we'll be estimating a proportion pi using a sample proportion p. After talking about confidence intervals a little bit, we'll also talk about how to determine sample sizes that will achieve a certain level of, error if we haven't actually done our study yet. So let's dive right in here. Confidence intervals for the proportion pi. We're only going to cover the large sample case. So with proportions, we'll only have to deal with one distribution. When we were talking about the sample mean, estimating the population mean, sometimes we use the t-distribution and other times we use a z-distribution. But for proportions, we will always use a z-distribution. So that will simplify things a bit. Some notation, we can denote a proportion as a certain number of successes divided by however many trials we've performed. This point estimate is an unbiased estimate of the population value pi, meaning that the mean of a bunch of sample proportions should equal the population proportion. Just like the mean of a bunch of x bars tends to equal the mean of a population. The same property holds for proportions. We also have the standard error, which is the standard deviation of our sample proportions, which should look somewhat familiar to our formula for the standard deviation of a binomial. This stuff has a binomial feel because if we're investigating a proportion, you are either part of the successful group or you're not. So it's not surprising that this standard error formula looks a lot like our standard deviation formula from when we were studying the binomial distribution a while back. Once we have this standard error, it sort of fits our format for making a confidence interval. Basically, it's your estimate plus some probability factor, which is a z-score or a t-score, and then we multiply that by the standard error. That's the form of a confidence interval. So in this case, our error will be some critical z-score, z subscript alpha over 2, and then we multiply that by the standard error, which, notice above, we had pi in the theoretical form. Well, we don't know what pi is, so we'll have to estimate that with p. So this is our error formula for determining a confidence interval for the population proportion. In order to use this formula, we do have to meet at least one condition, and that's that our sample size is large enough. And to determine if the sample size is large enough, we use the same rule that we used back in the binomial distribution when we learned that the binomial distribution tends to look like a bell curve as long as we satisfy the condition that NP is greater than or equal to 5 and NQ is greater than or equal to 5. So as long as both of these conditions are met, we can then apply this formula. So we should always check that first. Basically, this is allowing us to use this Z distribution. Our probability factor would have to be a binomial distribution factor if we weren't meeting these conditions. But once we meet these conditions, our binomial distribution will be enough like a normal distribution that we can use a Z distribution for our calculations. So it's pretty nice, pretty easy. We're really good with the Z distribution. So now, going forward, we can sort of do confidence intervals for virtually anything. I just have to give you, what are you studying? What probability factor should you use? And then I'll give you the formula for standard error, and away we go. So here's a little example. We have 626 Society of Economic Geologists members. So that's our sample size. And we found that 246 of them had their employer pay their annual membership dues. So the proportion of employers who pay membership dues in our sample is 246 out of 626. Now, this is a big, group, so this is certainly a sample from that group. We'd like to estimate the proportion of members who have their employer pay their membership dues. Basically, what is the proportion for the whole population? We know the proportion of our sample. It turns out to be about 39%, 0.393. So now we're going to basically add an error term to this percentage or probability. But before we do that, we have to check our conditions. In order to construct a 95% confidence interval, we have to first satisfy, is NP greater than or equal to 5? Is the sample large enough? And this will detect that. Our N in this case was 626. Our P is 246 out of 626. So we get 246, which is certainly greater than or equal to 5. So that part checks out. Now let's check out NQ, which is just Q is 1 minus P. We have 626 times 1 minus 246 out of 626. Doing that calculation, it's 626 minus 246, and it's the other half, so 380. I guess it's not half, but it's the proportion of people that don't have or it's the number of people in that group who didn't have their employer pay their membership dues. But it was greater than or equal to 5, so we're all good to go. This tells me that I get to use the Z distribution. The sample proportions are following a normal distribution. And that allows us to use the formula that we came up with up above. The error is a Z score, or critical value, times the standard error, which is P times 1 minus P all over N. And now, basically, this formula is really easy to calculate. We just have to figure out what the Z score is. In this case, 95% confidence means that our Z score, or critical value, is going to be pretty close to 2, the empirical rule. And if we actually look it up in our table, Z alpha over 2 is on the axis here. Basically, these are the cutoffs between what we expect to happen, what's likely to happen, and what's less likely to happen. 95% of our values are in the middle, and then we have 0.025 in the tails. And looking at 0.025 in our negative Z table, we've done this even in this lecture, negative 1.96 and positive 1.96. That's our Z score that separates what's likely to happen from what's not so likely to happen. So we'll use that as our factor. Go through our calculation here. After punching this stuff into your calculator, you end up with 0.03826. So roughly 3%, well, roughly 4%, I guess. We could say it's 0.393 plus or minus 0.038. I only studied 600, so I probably shouldn't go to the thousandth position. Maybe I should say 0.39 plus or minus 0.4, or 0.4, sorry. At 95% confidence. The nice thing with proportions, we don't have any units, so we can't lose any marks for forgetting units. I guess if you could convert these to percents, 39% of employers pay membership dues to this society, plus or minus 4%. Or maybe you'd like to, write it as an interval notation. 35% is less than pi is less than 43%. It's weird to keep writing, percent, and then say at 95% confidence. Sometimes I'll see people will write, instead of 95%, they'll say 19 times out of 20. In fact, they usually write it out. So if you ever see a survey result, say on the news or something, they'll often add that clarification rather than have percent. Just is kind of awkward to read. We're 95% sure that the actual proportion of employers who pay the membership dues into the Society of Economic Geologists is somewhere between 35 and 43. It's pretty wide. We can narrow that down by increasing n. So if we sampled, 2,000 of these, members of the society, our range would get narrower. We'd come closer and closer to estimating the actual value for the population. So yeah, that's how you do these. I'll show you in Excel. Sadly, there is no Excel function that just automatically does it. There's no confidence dot proportion function. You'd basically have to do what we just did in Excel, but it's not. I made you a template. That way, if you ever have to do another one of these, you could open this template up and basically just change the numbers for whatever problem you have. So here's a recap of what we just did. We had 246 successes out of 626 members. I calculated the proportion by just dividing. I checked my conditions. They were both greater than or equal to 5. That told me that I get to use the Z distribution. Then we looked up our confidence. It told us to use 95%. Calculated the Z score using Excel. It was norm.s.inv, and it gives you a negative number. So I put the abs for absolute value to make it positive, and we get our 1.96. And then sadly, this function isn't just built into Excel. So you have to kind of build your own custom formula for this, where you're going to take your Z score and then multiply it by the square root of all this stuff, which isn't bad. Here it is for my formula. If you're ever doing another one of these, as long as you keep everything in the same spot, you could basically just change, whatever the confidence is, change your X and your N, and it would automatically calculate this for you, as long as you don't move too much around. And you match the same answer that we had when we did it the by hand version. So Excel doesn't help you as much on these compared to confidence intervals for the mean, but it's still it doesn't, you don't have to worry about any intermediate rounding or anything. It just keeps track of everything for you. And then at the end, you can do your, round it to whatever you think is most appropriate. So yeah, that's confidence interval for a proportion. We might be wrong. There's a 5% chance that the proportion isn't in that interval. And that isn't because we did something necessarily wrong. We just got unlucky. When I sampled the members of the society, I just happened to get, a lower than usual number who, have their membership dues paid. Remember when we were doing the mean, we came up with a way to estimate sample size. Basically, what do you do if you haven't collected any data yet? You can come up with a lower bound for what sample size you need in order to achieve a certain amount of error. And we do it the exact same way we did with when we were studying the mean. Basically, we take our error formula and just rearrange it. Solve the error formula for n. A little bit of algebra, square both sides, etc., etc. You end up with this formula here. So we have, as long as n is greater than or equal to this, we'll achieve whatever level of, error we desire. The only problem with this formula, you might notice, is that this is the sample size that we need in order to accurately come up with a confidence interval for pi. Yet the formula itself has a pi in it. So we're going to have to come up with some way to deal with that. Remember when we were talking about the mean, we would just sort of make up a number for the standard deviation in that formula, and we just make sure we erred on the high side, or we'd take a little pilot study and hope that standard deviation erred on the high side and then gave us a large enough. In this case, we just want to err on the high side to make sure that we get a large enough n. So one way to do it is, again, maybe you have some old data. Maybe you have some historic data that would give you some insight as to what the proportion might be, and then you might use that in that formula. So I'll rewrite the formula here. It was z alpha over 2 squared times pi times 1 minus pi all over e squared. We can get the z score if we're going to continue to be 95% confident. The z score is just that, we're going to be real familiar with 1.96. And now let's see, what degree of error do we want? It says, suppose you want to estimate the proportion of members who employer pays their membership dues, and we want to be within 0.01 or within 1%. In the previous example, when we did it, our error was 4% or 3.8%. So I know that this number is going to be bigger than 626 because 626 only got us down to roughly 4%. So to get down to 1%, what sample size would we need? So my error will be 0.01. And now, what should I put for pi? I don't know what pi is. It's the whole point of doing the exercise. But maybe you know from some other sources, like maybe the American Mathematical Society has some good data and they know the percentage of employers who pay membership dues. Or maybe there's some other geological society where they know something about the percentage. So suppose in this case we know that from other studies, it's estimated to be around 40%. Then we can just use that and hope for the best. Doing a little bit of calculation there, you get 9,219.84, and then we'll round up. So let's make sure n is at least 9,220. If we sample 9,220 of these members, we'll get our error down to 1%. I mean, is it worth the cost? With 624, was it? We were able to get the error down to 3.8%. We have to do so much more work to get it down to 1% that it might not be worth the cost. And we might still be wrong. This might not, technically it might not be a large enough sample because we sort of made up a number here. We just sort of took what we knew, 40%, and we hope for the best. That might not be the best way to handle this in a more scientific study. So we could take another approach. I call it the pessimistic approach. Basically, I'm trying to find an estimate for pi times 1 minus pi. I want to put something in for that. Well, if I could replace that with the maximum it could ever achieve, then I'll always make sure that my sample size is large enough. So what is the largest thing that pi times 1 minus pi can ever be? And keep in mind that pi is a proportion, so it's between 0 and 1. So I plotted that. I wrote a function, y equals pi times 1 minus pi. Here's my pi axis. Here's my y axis. It's a parabola. Y equals pi minus pi squared. You can find the vertex of that thing and find the local max. Or if you're, a math nerd, you could take the derivative. It's 1 minus 2 pi, and then set that equal to 0. Remember, pi is just a variable here, and then pi is equal to 1/2. That's its critical value. And then you do the first derivative test to see that it's increasing before that and decreasing after that, and you get your local min at 0.5. So what is the value when pi is 0.5? Well, that's 0.25. So the largest thing that pi times 1 minus pi can ever be is 0.25. It happens when it's a 50-50 chance. That's the hardest one to predict. So we end up with that bound of 0.25, and then we can just replace that into the formula. So our formula gets, really simple here. It's just hard-coded. It's always just 0.25 times Z alpha over 2 squared over E squared. Let's repeat our error example using that. Again, we wanted to do the same problem where we're doing 95% confidence, and we want to keep our error down to 1%. What sample size do we need in the pessimistic approach? Well, just plug in 1.96 into our formula, plug the error into the formula, and leave that 0.25. That's just a constant in the formula. We get 9,604. When we did it using the guessing method, it was 9,220, which is quite a bit less. Almost 400 people less you'd have to contact. But using 9,604, we'll make sure that we do achieve our 1%. Our error will be at most 1%. It'll, possibly be less. The disadvantage of this method, the pessimistic approach, is you might need to study more than you need to. The advantage is you'll always study enough. When you use the other method where you're sort of guessing, it might save you money. So that's why it's out there as an option. But you might not end up ultimately studying enough because, well, you estimated an important part of the equation. So that's how we collect the data in order to basically study a population parameter. What sample size do we need? So now we've done that for studying the mean, and we've done it for studying for proportions. Remember, we'll use Z distribution when we're studying proportions. And when we're studying the mean, when we did the mean, sometimes we used Z and sometimes we used T. But when we did proportions, we just always use Z. In real life, the mean is almost always studied using T because we use T when the standard deviation isn't known, and that's almost all the time. So basically, if you remember that you use T with mu and you use Z with pi, you'll be set. Of course, that's on your formula sheet. So you won't be left wondering, what's going on. I think that's enough for this section. We'll continue on next time with hypothesis testing for both the mean and proportions. So I hope you all have a good day and take it easy.